Modern computational biophysics has largely moved beyond studying isolated proteins in a vacuum. The objective now is to simulate complete, biologically accurate environments. These native environments are incredibly dense and chemically diverse. A single simulation box often needs to accurately represent transmembrane proteins embedded in lipid bilayers, coated in carbohydrate chains, and interacting with nucleic acids. There is no single universal force field designed to handle all of these materials at once. To build these systems, researchers are forced to mix distinct parameter families, stitching together models built by different teams for different purposes. When you drop these mixed parameter sets into a molecular dynamics engine, the results are often disastrous. The simulation box can violently destabilize. Lipids undergo non-physical phase separation, proteins fray and unfold, and the surrounding water and ions rapidly crystallize into solid blocks. You can take individual components that are perfectly parameterized in isolation, but if you ignore the mathematical boundaries between them, the entire system will spontaneously fail. The root of this failure is a misunderstanding of what a force field actually is. Parameter sets are not collections of independent absolute physical constants. They are highly co-optimized thermodynamic ecosystems. Every charge, bond length, and van der Waals radius is calibrated against the others within a strict set of internal assumptions and mathematical scaling rules. In software development, we rely heavily on modularity, the idea that you can swap discrete components in and out without breaking the program. That plug-and-play logic does not apply to the physics of molecular interactions. Achieving physical stability in a heterogeneous simulation requires systematically calibrating the mathematical boundary conditions at every single molecular interface. Preventing simulation artifacts requires strict mathematical hygiene, ensuring that the rules governing one molecule do not corrupt the physics of its neighbor. To see exactly how these boundaries break down, we will build a heterogeneous system from scratch, starting with a single protein suspended in a vacuum. We first introduce explicit water molecules and monovalent ions. This forms the foundational solvent-ion triad, dictating the thermodynamics of everything else we will add. This baseline introduces our first strict boundary condition. Ion parameters are acutely sensitive to the specific water model you choose. A common error occurs when developers mix ion parameters optimized for a weakly structured water model like TIP3P and deploy them in a highly structured model like TIP4P/2005. Because the electrostatic topology of the new water model differs, the ions fail to solvate correctly. The individual ion hydration-free energy error margin skyrockets to 8%, corrupting the solvent shell. Our first integration rule is that developers must respect this triad by selecting water-specific ion sets designed natively for the chosen solvent. To further stabilize the triad in concentrated solutions, developers often use scaled charge models for monovalent ions, reducing their charge to plus or minus 0.85. This approximates the dampening effect of electronic polarization without the immense computational cost, preventing the salt from prematurely crystallizing. Before introducing any complex macromolecules, this baseline solvent ecosystem must be thermodynamically balanced to prevent structural artifacts from cascading upward. Next, we surround our protein with a lipid bilayer, observing how the transmembrane domain physically inserts into the membrane environment. This creates an immediate mathematical friction point. Different force field families calculate the physical collisions between atoms using entirely distinct Lennard-Jones combining rules. Amber uses the Lorenz-Berfallout arithmetic rule for collision diameters, while OPLS-AA uses a geometric mean. These create distinct potential energy wells. If a single global rule is applied, it corrupts cross-interaction potentials. One molecule obeys the other's physics. Notice the red X marks for Gromos 54A7 and Amber 14-asdene-slipids in this chart. Mismatched parameters fail to predict correct membrane insertion depths. As seen above, incorrect rules push peptides out of alignment. Developers must override global settings using pairwise exceptions. Manually assigning the correct math at the boundary is the only way to preserve the validated properties of the protein and the lipid simultaneously. We now attach a highly flexible hydrophilic carbohydrate chain, a glycan, to the surface of the protein. This introduces the challenge of 1,4-dihedral interactions. These are the electrostatic and van der Waals forces between atoms separated by exactly 3 covalent bonds. To accurately capture the inherent flexibility and ring-flipping dynamics of carbohydrates, their specific force fields require precise numerical scaling factors applied to these 1,4 interactions. If you apply a single global 1,4 scaling factor across the entire hybrid system, compromising between the protein and the carbohydrate, you inherently destroy the conformational sampling of one of the molecules. The carbohydrate will either become completely rigid or the protein backbone will destabilize. This brings us to the third integration rule. Developers must strictly isolate intramolecular scaling to prevent cross-contamination between molecule types. In practice, calculate scaled values in advance, writing explicit pre-scaled pairwise parameters directly into the configuration files for the specific molecules that need them. By rendering these scaling factors strictly local to the specific molecular domain they were designed to govern, the system retains its overall thermodynamic stability. Finally, we introduce a nucleic acid strand interacting directly with the positively charged basic residues of the protein. This boundary exposes a documented flaw inherent to fixed charge force fields when handling protein nucleic acid complexes. Severe electrostatic overstabilization occurs between basic amino acids and the negatively charged DNA backbone. The DNA strand physically warps and frays under the intense attraction. This unnatural overbinding locks the molecules together, severely restricting the conformational dynamics that govern how the complex would actually behave in a living cell. This necessitates the fourth integration rule. Researchers must systematically calibrate interfacial cross-interactions using established corrective frameworks. One proven method is to slightly modify the phosphate-water collision diameter. By manually adjusting this specific Lennard-Jones parameter, you can balance the hydration forces against the electrostatic pull, stabilizing the interface. Standard non-bonded interactions simply cannot be trusted out of the box at these highly charged interfaces. They require explicit recalibration to reflect physical reality. We now have a fully assembled, chemically heterogeneous system operating in thermodynamic harmony. The isolated thermodynamic ecosystems of the protein, the membrane, the solvent, and the DNA have been successfully bridged, entirely because we strictly enforced their local boundary conditions. This plot graphs the free energy change of the system over a simulation. The linear progression of the Coulomb and van der Waals delta G lines proves the system is experiencing a stable, predictable thermodynamic state change, free of structural collapse. The ultimate proof of a valid mix-and-match strategy is exactly this, a stable macroscopic thermodynamic profile that derives entirely from corrected microscopic boundary conditions. Looking ahead, the field of computational biophysics is moving away from these manual mathematical overrides. Next-generation computational frameworks, like adaptive force matching and differentiable molecular simulation, are beginning to automate the co-optimization process. Instead of tweaking a single collision diameter, these engines use automatic differentiation to optimize parameter sets directly over nanosecond-length trajectories, locking the variables into alignment. Their primary advantage is the profound ability to simultaneously fit hundreds of parameters against both detailed quantum mechanical reference data and macroscopic physical observables, like liquid densities and hydration-free energies. But until unified, fully polarizable force fields become computationally trivial to run, researchers must rely on rigorous integration workflows to map complex environments. Mathematical hygiene is the absolute requirement for ensuring complex biomolecular simulations yield insights into physical reality, rather than just generating temporary software artifacts.